Beyond his scientific achievements, he has played a vital role in mentoring young researchers and advancing astrophysical research in the country. So please join me in welcoming Professor Srianand.
Good afternoon. Today I will discuss at an elementary level what we mean by forming a galaxy and what are the challenges involved if you try to form early galaxies, and if time permits I will just highlight some of the attempts we are making at IUCAA. So I thought that it is, since it is a astronomy club and other things, I'm not going to go very much into complicated physics, but I will try to explain them in words. Okay? But don't carry this message that we are just doing everything in hand waving, which is what I will do today. But one of the purpose of giving this talk here is also to excite some of you to take up such challenges in astrophysics, because you will try to see this. So the title says that challenges in forming galaxies, so I will spend enough amount of time to just convince people what you mean by forming galaxies. And it will be very different for different people, but for me I will define what do I mean by forming galaxy. If somebody asks me to form a galaxy, what are the things I have to do? That's what we will do. Then 100 million years, that is another point I will bring up. What is the meaning of, why do we worry about this first 100 million years? And in that sense, it is linked to James Webb telescope's observations, so that is the kind of connection to the title. So most of the time it will be like very many things which you know, but I will put it in kind of a argument so that you will understand what we are trying to do. So if we ask what are galaxies or what is a galaxy, it is very easy for us to define it. Galaxy is kind of, if observationally, if you want to define, you go and image the sky. Whenever you find some point-like object, it is most likely star in our galaxy. But if you find the diffuse light which has some pattern, we will call it as galaxies, and our understanding is that this is a collection of stars which are arranged in a particular pattern. Okay? So if you take a textbook and ask, what do I need to do about galaxies? You will study that galaxies come with different morphology. Our idea is to see how you can assemble stars into different morphologies. Of course, the problem is severe, because if I ask you to assemble certain things in particular shape, you will do it, because you are the person who is going to employ force on the material which is available to you. And since you have full control over what you can do, you can produce any shape of your interest. But when you are looking at the sky, it has to happen on its own. So this is the problem. We have no control over what shape you are going to get, but you are going to get different varieties of shapes, so we have to decide what kind of initial conditions that can lead to these shapes. So this is the game we are playing in astrophysics. Unlike in any other scientific branch, we are going to see something and we are going to understand how you get such a thing which are occurring naturally in space through some physics which we understand, modulo some initial conditions. Okay, so that's what it is. So we'll start with this. The first point I want to emphasize is that galaxy itself, whatever we call as the shape or whatever we call as the structure, itself is a bit complex, because that's what is illustrated in this figure. This is the image of the same galaxy taken at different energies. Okay, so typically this is what we know. This is kind of optical image of a galaxy, and you already see that there are kind of structures which you can follow. Our eye easily follows the structure. It's much easier than artificial intelligence, because real intelligence follows structure without guiding anything. But we can also see there are certain spots which are bright, certain spots which are dark or brownish in this plot. So definitely challenge will be to get this structure and make sure that certain regions are bright, certain regions are dark. Again, I will just give you kind of problems an astronomer will face. If you find certain regions are bright, you will say that these are the regions where we are seeing the starlight. It's very easy for us to. So if there is lot of brightness in some region, you can say that there are lot of stars there. But there are regions where you find these dark patches. What do you mean by that? Here is the problem. Either simplest conclusion is that there are no stars there, or the stars are there, you are not seeing. It's like I put all the lights. If I go outside, I cannot guess whether the light is there or not, because these walls are not going to allow these lights to penetrate and go other side. So whenever you see such a thing, you have at least two interpretations. One is that there are no stars, or there are stars which you are not seeing. So already you see this is the, so that is well explained in this plot. So we are going, if you go towards the lower energy, if you go and look at the same galaxy in X-ray, radio, you find the emission roughly follow the structure, but the structures are very different. Okay, so that is one thing we can notice. And similarly, if you go to the other extreme end, this is where you have X-rays, and again the galaxies look very different. The point you want to say is that when you go to different wavelengths or different frequencies, you are asking the question how photons are created in that region. Okay. So another important point you need to understand in astrophysics is that whenever you receive light from some region, we need to understand that that region is losing some amount of energy. So that's the first point. So all galaxies cannot continuously lose energy and all the time bright also. Okay. So definitely whenever you see some regions are losing energy, they are losing energy because they can afford to lose energy, because they are also creating similar amount of energy in the same region. So these are the kind of logic one has to follow. And clearly the fact that if I go to different frequencies, if I tune my specs to different frequencies or different wavelengths, the appearance of the object is very different. That means if you join together, a galaxy will have different set of emission mechanisms, right? Different set of emission mechanisms which will give you different kinds of patterns depending upon which emission mechanism dominated different wavelengths. Simple example, if I want to generate X-rays, the physics I will use is not necessarily the same physics of nuclear reaction going on in the centers of sun or centers of stars, and that has been sort of transported outwards and become like a visible light. So this is the first point. So galaxy formation means in addition to getting the structure, we have to make sure that emission mechanism works correctly. Means like I should be able to explain the same thing like the way you see in reality. I should be able to tune my frequency to different wavelengths. I should still see what kind of patterns which are emerging. So that's the first point. Okay, so that means you are already understanding that forming a galaxy is not just getting collection of stars and putting them somewhere. So it involves the fact that X-rays are emitted. That means I need to have some mechanism which accelerates charged particle to very large velocities. This highly accelerated charged particle will emit radiations in X-rays. Okay, that's the mechanism you have to follow. Second thing is that whenever you want, so what decides this pattern? Now I have to understand. I see some pattern in the stars, and what decides this pattern there? So can I take galaxy as an isolated entity? Can I take the galaxy as an isolated entity and just to look at what all happening? Some processes are going on, something is added, something is subtracted. Can I do like that? Or I have to worry about more than what I see? So here is an example. It's again a famous group of M31, 32, 33 galaxies. And if you just see in optical image, you see three different galaxies which are like nothing special in this region. The same region you go and observe with 21 centimeter. This 21 centimeter is nothing but the transition occurring in the hydrogen atom. This is like a ground state hyperfine transitions. If you look at this emission, this is what you see. You can see at least roughly you can identify three galaxies here. One here, one here, one here. That matches exactly at the three locations. But you also see that the gas is just connected between them. So this is again, there are two things I learned from here. When you form galaxies, you will not be worried only about stars, you should worry about gas also, because of course, star is nothing but a condensed gas, if you want to see that way, right? So we should do that. Second thing is that, looks like, even though the stars are tightly bound and probably a tidal interaction of a neighboring particle on a star may not be that important, but the gas in the same galaxy may be interacting strongly with the neighboring galaxies. Since gas is an ingredient which is important for forming stars, these interactions also have to be taken into account if you are interested in forming stars in galaxies. Okay, this is the first point. So basically we are thinking of first of all, we are thinking of stars, how to form stars. Second thing is we are thinking of what is the surrounding regions of stars, because they decide what kind of emission you will have. You will have gas. You may have highly ionized plasma because you are seeing X-ray emission coming from these galaxies as well. So this is the second point I wanted to bring your attention to. So again, the same thing if you do it in bit more detail. So it was an early image taken with very large array. Later on, the same experiment was repeated. It was observed some 10 times deeper. So now the same picture. Here you can say that are they really connected, or you are imagining something like that. People went further, and this is the same image. Now you see that there is no ambiguity. It is nicely connected. Not only connected, you can also start seeing some blobs which are appearing all over the place. These are the gas clouds which are not related to any one of these galaxies particularly, but you can also see them appearing. So these blobs are known as high velocity clouds. So they are not in the plane of star forming region. You can also see big clumps which are floating around the galaxy. That means you can visualize the galaxy like this. There are also some gas clumps which are off-planar with respect to the disk itself. One of these guys, MIT2, again, MIT2 is very famous. If you go into MIT2, and this is the blown up image of MIT2, I'll just see what is being plotted. This white color is the pure light, stellar light coming from this galaxy. Then you put a filter which is tuned towards the H alpha line. What is H alpha line? H alpha line is the Balmer transition, 3p to 2s transition. So it is around the optical wavelength, right? 5893 angstrom. So what you do is that you put a filter. So only photons in that energy will come into this imager. Okay. So you make an image of that. So it's very interesting. If all parts of the galaxy has hydrogen, and if they are uniformly emitting whatever you call H alpha, you will see everywhere, right? But if H alpha is preferentially coming from some region, you will not see any stellar light from that region. So this is very obvious, and you can, if I motivate you a little bit, you can see kind of a cone here, and the red color thing what you are seeing is basically the emission coming from the hydrogen atoms. So this has been now understood. Of course, we can do further. If you know hydrogen atom, since it is atomic transition, it has a specific wavelength. We know exactly, we can associate which wavelength at which this transition is occurring. Now if you do spectroscopy very carefully, the line may not come at the same wavelength as you have in the laboratory. It can go upward or downwards. Based on that, you can actually decide what is the kinematics of the gas. Okay, that is very interesting. So what people found is that it is not only looking like a cone, the gas in this cone is also traveling with large velocities. It's like an outflow. So this is a picture, but this is very important physics. One realizes now, one has to incorporate when you are thinking of forming a galaxy. It is inevitable that certain activities, you are forming stars. So what happened to a typical star? A typical star will live for some characteristic time. Afterwards, it will die. What is the meaning of die? Physics-wise, a star is a hydrostatic equilibrium. You are producing enough energy which is going out and pushing the gas outwards, and the gravity is holding on to it. Anytime you violate this condition, either you switch off the nuclear reaction, or you overproduce nuclear reaction compared to whatever is keeping the balance of the star will be disturbed. Okay? So this is what leads to variable star, pulsating stars, and things like that. The extreme end is that you switch off the nuclear reaction in the center, the whole gas will, in the outer part, will fall into the center, but it cannot go to the whatever zero or delta thing. At some stage it will hit a core and it will bounce back, and this is what we call supernova 2A. It's called core collapse supernova. So this is one of the ways in which a typical massive star will die. Of course, death of the star is okay, but what happened to this bouncing gas? Bouncing gas carries roughly 30% of the total mass which is available in a star, and it carries 10% of the binding energy. Okay, in CGS unit it is like 10 to the power 51 x per second. And if you want to understand what kind of speeds at which, if you take one solar mass of few times 10 to the 33 grams of gas, traveling with 1000 km per second. You can visualize what kind of momentum this guy is carrying. If you want to visualize, want to have some other feeling, if you wait, say if some material is going with high speed, it will try to push whatever is around, right? It will try to push them around and move them. It's like a broom going through the dust. So it will carry the dust and move, okay? So if you wait for say 1 million years and ask how much mass a typical supernova can lift it outside. So you can just ask, if I send a supernova into some surrounding region and they just keep pushing, I ask it has gone for about 10 to the 6 years, and just ask how much it would have lifted. It can lift about 1000 times mass of sun. It's coming from few times mass of sun, but it can lift about 1000 times mass of sun. It's pure conservation of momentum, because of the speed at which it is coming. It can lift quite a bit of mass because it carries sufficient amount of momentum. So this is what we have to do. So if you think of one supernova lifting 100 times or 1000 times mass of its progenitor, imagine I put some couple of supernova together, some 10 supernova in a clumped region, it can completely lift your gas which is bound to the galaxy and throw it out at high speed. So this is what is known as galactic wind driven by supernova. Okay. So this is the process which we have to envisage, because what happens? This is removing gas. When you form a star, when it dies, it removes the gas in the surrounding region, which means the subsequent formation of stars will be stopped. So if I want to build a big galaxy, I have to make sure that I have some energy and mass and everything available so that continuously I keep forming stars, right? If I cannot do this for some reason or other, I'm going to switch off and that's it. It will disappear like a blob of gas staying somewhere. So this is another physics you have to incorporate. That means first you remember, I need to have all sorts of plasma in my galaxy so that I see multi-wavelength. Any wavelength I go, I see some light coming from there. Something has to keep the galaxy into this multi-phase plasma. I'm just shifting to slightly higher language. Second thing is that in this particular thing, we should also worry how this plasma will be affected by star formation which is going on there. It can be thrown out or whatever. In addition to that, we should also worry about what another neighboring galaxy will do to this plasma. Whether it can strip off, whether the galaxy will fall in. So this means that this is what makes galaxy formation an interesting problem. It is not a simple problem. It used to be a simple problem when observations were limited. Now that we have detailed observation, the simple way of forming galaxy, in my opinion, no more works. So we have to worry about this. So next we come to, this is a standard problem, all of you should be knowing, so I should go rapidly. Next thing we know is that all the matter we see with our eye or with any telescope is not the only thing which is available. In fact, it is one of the, what you call, not the strongest component in the galaxy. It is 1/6 or maybe 1/100 in typical galaxy. It's constitute of matter which we see and which we feel. But if you look at the rotation curve of a galaxy, what do you mean by rotation curve of a galaxy? I go to the center of the galaxy and I pick gas particles at a radial distance, in this distance, okay, semi-major axis. I pick different gas packets of gas, and start measuring what is the velocity at which the gas particle moving towards me. This is called line of sight velocity, because you just take the spectrum, just find where are the wavelengths, then ask how much is the wavelength shift. That gives you the velocity with respect to you, how much velocity at which it is moving. In fact, it is interesting, people found that if you take a galaxy, this is the distance from the center, and if you plot the average velocity, and velocity increases with increases with distance, and it becomes absolutely flat. This is opposite of what we know from Kepler's law. We know that if you have a central mass with a central force system, as you go further and further out, the velocity will slow down because it will go as 1 over r. Okay, m over r. So it is clear that if there are two ways of looking at it. One, you will say that okay, forget that gm over r is not the thing I am interested in. It may be something else. Okay. Other way of saying is, if you want to align yourself within whatever Newtonian mechanics we have done, then you have to say that the only difference is that in the problem like planetary system, there is a center of mass which is dominated by one single object. Okay, but if you relax that condition and say that galaxy, if I ask what is the mass of the galaxy, it depends on where, up to what radius I am measuring. If I go very close to the galaxy, the mass I will feel, or gravitational force I will feel from the galaxy will be limited to mass inside that radius with respect to center of mass. So as I go further and further, if I want to satisfy this condition, whatever dilution I am getting based on radius should be compensated by mass. Okay, that means I have to set up how the density falls as a function of galaxy to make sure that that thing goes straight. That leads us to believe that even several times beyond whatever we see as the optical edge of a galaxy, you have mass distribution, which we don't know what it is, but we want it to interact with every other thing by mass. Okay, so this goes by the name dark matter. So this is a problem. So there are two ways of addressing this problem. One is that you devise a new force law. This is called MON, modified Newtonian dynamics. Or you say that like I will introduce a new particle or new system which I will not see it. It will not interact, it will not emit in X-rays, it will not do anything. Of course, people want it to emit in all wavelengths, but as far as we are concerned, we will say that dark matter is there, which is like only, we will feel it by mass only. We will not have any other interaction with it. So now we understand, in addition to this, I need to produce I need this setting to be in the gravitational potential. So this brings us an interesting problem. I go back to the same thing I said. If you want some shape, you can ask your colleague to align it. If I want to make a sphere, I will know how to make a sphere. If I have to make it as a square, I know how to make it as a square. So I have freedom to apply forces at the right direction. So we said like if you want a galaxy to be having particular shape, I need to do it with some force which we will believe is going to be gravity. So we were thinking of how to do it with gravity and all. So now we are saying, in a typical galaxy, the dominant source of gravity is not what you see. The dominant source of gravity is not, you don't see. So you have to start with something which you don't see. We don't have any understanding of physics. That is going to govern the internal gravitational dynamics of that system into which these star particles are going to move. So that means it's clear a galaxy formation should involve some dynamics of dark matter particle into which these guys will be tracers, because this mass is 10 times more, roughly 6 times more than whatever you can get from our baryonic matter. So you can even treat baryons as just tracers of whatever is the gravitational interactions which are governed by the dark matter particle. So this is the kind of settings we will be in. I am just putting a setting. Okay, it's highly biased statement. So you can always question each one of my statements because this is research, right? So, but I will guide you through some kind of setting so that you understand what we are doing. The next interesting problem which happened is related to what happens in the centers of a galaxy. Every galaxy, if you go to the center, now it is known that the density of particle or mass density becomes extremely large. This is the correct statement. Okay, but we interpret this as every galaxy having a black hole in the center. Okay, so this is the, of course we are now getting a proof that the density, highest density peak you are having in the center is actually a black hole through some direct imaging you are seeing these days for some of these nearby Einstein telescope, for example, allow you to give you this. Okay, even horizon telescope. So the point is that every galaxy has a central region, and in special galaxies, what is known as active galactic nuclei, if you calculate the luminosity, that is energy per unit time released from this object in the central region, very central region. So if you want to have a size, again it is important for us to realize the size. What I mean by central region is typically the distance between us and sun. Okay, so 10 to the 13, 10 to the 14, maybe in a best case 10 to the 15 centimeter with respect, that's the central region of the galaxy, only that much. And you know a typical galaxy is spread about 10 kiloparsec. 10 kiloparsec is what? 3 times 10 to the 24 centimeter. So you are talking of a region which is 11 orders of magnitude smaller than the whole galaxy itself. 10 to 11 orders of magnitude smaller. But if you calculate the total luminosity coming from such active galactic nuclei can be as much as the total galaxy itself. So this is what is an interesting problem. So that's what leads us to believe that we all galaxies have a central black hole. So how do you know all galaxies have a central black hole? There are two methods by which people conclude this. One method is what I talked about. You just look at the energy per unit time coming from the central regions. How am I doing with time? Okay. From the central regions, then just convert that energy and see how you can get. The physics involved here is when you go close to the black hole, the gravitational potential changes very rapidly. I mean the gradient of potential is steepest close to the black hole, and force is nothing but gradient of potential. So that's where you extract maximum amount of energy for a given mass when you are at the densest region, because density for a given mass, dense you are, the potential gradient is steeper. So that's exactly is what is being used. This is one way of doing. Another is that like our galaxy, if you go and look at the stars in the central region, they don't stay like this. In fact, they move faster compared to stars which are slightly away from the central region. So you can now track the stars, and you can actually see like the way we do Kepler's problem. You just see that stars going around and filling an orbit. If you know collection of 50 stars, and we can fill orbits of all 50 stars and find out where is the focus. That focus will give you the location of the black hole, and this is how it has been done for some of the nearby galaxies. So what we know is that literally all galaxies have black holes. Some galaxies have black holes where matter fall into them so that they shine. If there is a black hole, nothing falling into the black hole, you will not see it. Okay, that's a perfect black hole in textbook. Okay, nothing is there. So black hole will not emit, or even if it emits something, we don't care. At least astrophysicists should not care. Theoretician will care about that small amount of energy which will be released. Okay, we will not worry about it. Okay, this is the thing. So now we introduce several components. Plasma, we need to have dark matter, right? Dark matter will cover everything, and we have introduced what is black hole. Okay, so all can be independent. Can all be independent? Then no problem. If they are not connected by any physics, you have no problem. But the problem is when people plot, actually this is the equivalent plot. If you plot mass of our galaxy, don't look at what I have written down, but just listen to what I am saying. This is equivalent, this is the proxy for mass of the galaxy, and this is the proxy for black hole mass. So you find a tight relation. In fact, this is tight when it comes to astrophysics, but maybe like in pure physics you will see scatter can be zero. So here it's a kind of you can see it's span over some 4 orders of magnitude here and about factor 5-6 here, and you can clearly see there is a strong correlation, which means bigger the galaxy, the larger is the black hole mass in the center. Of course, you say, okay, it is obvious. If you are rich, you will live in a bigger house. So why should you make this thing? But the main problem is that when you are talking of galaxy, you are talking of scales. Again, I go back to the scales which we discussed. The scales are like scales of 10 to the 23, 10 to the 24 centimeters. Whereas when you are talking of black hole, you are talking of scales which are less than 10 to the 13 centimeters. I am talking about event horizon, it will be even smaller if you are talking about collapsing into a smaller black holes. So this is clear. That means when I am trying to form galaxy, distributing them in some space with something with the right proportion of stars and gas, in the gas itself a right proportion of how much gas particle is in plasma, how much in neutral, because plasma will emit X-ray, neutral will emit 21 centimeter hydrogen. So I can clearly see observations are too many to have solid constraints in them. So that's why this relationship also brings us to something. That means even though AG or whatever black hole is confined to a smaller region, since it is so energetic, right? We said like this can produce energy or luminosity at a given time as much as what is produced by the full galaxy. That means it's extremely efficient energy producing mechanism. So can I couple, if I take small amount of energy, and in fact black hole may not be able to travel this 10 orders of magnitude difference in length, but if I propagate electromagnetic wave or some disturbance which travels at high speed, I will be able to dictate what happens to the galaxy compared to what happens to the central regions of the black hole. So this goes by the name feedback. Feedback means the process which is going to govern the growth of black hole should also somehow linked to the way you are growing the galaxy or vice versa. The process which you are using to grow the galaxy should somehow dictate how I am going to grow the black hole. Okay? So that process of growing the galaxy may involve everything I discussed. What happened to the outflows, what happened to the interaction with the neighboring galaxy. So that's why this problem becomes interesting. And also it is not easily trackable with analytical calculations. So we all tried our best to do all this with simple ideas of dark matter potentials and put gas in them and do various things. So it's what we are. So let me move on to the problem and good statement of the problem. Statement of the problem is the following. We want to start with actually the way we understand how we are forming galaxies is like this. In our universe there are some small fluctuations. Okay, there are some fluctuations where by random process itself some regions are denser compared to some other regions, because the random process can lead to denser region and rarer regions. These denser regions tend to become denser and denser because we are dealing with a force which is one directional. So once you created a denser region, the surrounding region will be attracted by this density peak and we start growing. So this is the idea behind galaxy formation thing from scratch. So something should create initial conditions, and I'm sure like you know that there are proofs of existence of initial conditions and all. I will not go into that. Just to keep it within the stipulated time, I will stick to whatever I wanted to say. So basically this is what is happening. You have fluctuation in the medium. Wherever the fluctuation is above some threshold, we can see that this fluctuation in the density field can grow, which means that it will start attracting material between them, and this can lead to what we call galaxy. Your definition of a galaxy can be very different, but theoretical aspect wise, what you will call it as a galaxy. So we will start from the simple case. I have a medium, but we are living in Big Bang model. What is Big Bang model? Everything is expanding. So this is what you have to remember now. If I take two particles, this particle will, if I see in an appropriate frame, I will see them going away from each other. But what we are talking about is that we are talking about bringing the particle together and forming some density enhancement. So it's always two competing forces. One is that the expansion of the universe is trying to make the particle go away from each other at some stage, but you have produced a density fluctuation. The density fluctuation in the overdense region or denser regions will try to grow. So two test particles if I take, and the kind of situation it will feel is that it will feel attracted by the mass between them in some sense. The effective potential between them will attract them. Gravity will pull them apart. Both are changing as a function of time. This attraction is going to keep on increasing because it's accumulating mass, if it accumulates mass. Expansion will also be decided by what kind of universe we live in. Rate at which we are expanding will be decided by what constitutes our universe itself. Again, so that if there is a situation, a test particle starts feeling only one force dominant over the other. In particular, if the test particle feels that it has to fall in, and it now no more worries about what is happening in the outside world, we call is a possible region where you can form a galaxy. That means whichever region, overdense region, where the dynamics of the particle inside is completely dominated by the local gravitational potential and nothing to do with the expansion of the universe, you are setting up regions which are potential sites of forming galaxies. Some people will call it as dark matter halos, some people will call it as potential protogalaxies, and whatever you call, but our definition is very simple. So we have to create this initial fluctuations should create various islands in our universe which are no more expanding with respect to the expansion of the universe. But this, if I consider two islands, again they will face the dilemma whether to come towards each other or they will be part of the expansion of the universe. So this is what is known as hierarchical studies. So at all scales this dilemma will be there, like the way we have dilemma, right? Whether to obey Earth. So we don't worry about gravitational force from anything else as long as we are standing on Earth. Once you start moving out, we will get problems, right? That's exactly like this. So that's the first point. The first point you understood, right? This is the creation of halos in a simple way. And just again, it's like at the level of pedagogy, this is what I can do. Having done this, now we want to create stars, so it cannot happen from dark matter alone. So what we do is that dark matter set up a place where matter can form and do all other things, because matter can interact, matter can do various things. So we can use these sites which we create as scooped out from the expanding universe, put gas particle. Of course, gas will naturally go in because gravity will keep some amount of gas with this. Then you play with the gas in each one of these isolated regions and try to build whatever we are thinking of doing. Of course, like I said, there may be several isolated regions. They themselves, if they are close by, they will start overcoming this expanse and start attracting. This is what leads to this mergers of interaction between three galaxies which we saw, right? So that will happen. So you will start building a bigger galaxy by two ways. One is that you start with very large mass in the beginning itself, or you start with reasonable mass but start eating up neighboring galaxies and becoming bigger. So these are the kind of scenarios which you can think of. So once the material falls into the galaxy, what we have to do? It's very simple to us. You look at the sky, you have gas, and you can see in the clouds, we have seen lots of patterns, lots of things can happen. Sometimes they are very dispersed, sometimes they are clumped. So exactly this is what you want to know. If I give you a lot of gas and I say form stars, what you have to do is that you have to make them into smaller regions where we can form stars. What is the meaning of forming stars? I have to take this gas particle, somehow I compress them into densest possible, I have to compress them to maximum possible density so that I trigger a nuclear reaction. There the gas particle become a star. Okay? Otherwise there is no point. So this is another condition. So I start with some gas, whereas dark matter will live like this because this is non-interacting. So it will just, two particles can go past each other, flux of particle can go, they will just feel only gravity because the positions are changing. They are not going to hit each other and interact in any other way. Whereas the same thing happened to two gas particle can interact in various forms. They can exchange energy and momentum when with the neighboring particle or neighboring region. So there could be lot of mixture of what you call phase-space distributions. Right? So clearly what we need is that first of all, if I want to bring gas to very large density, I have to resist the pressure. The best way to do is that make it as cold as possible. Okay, so that I can compactify the thing. So this goes by the name cooling. So you have to start with gas. Somehow gas has to cool. Okay. So cooling is what we see. This is what I come back to. If some region is cooling, you will know. Cooling means some photons or some way I am throwing energy from this point to infinity. The best way to throw is by electromagnetic radiation. That's the best way to release energy. So if some region is cooling, any radiation through which it is cooling, because every time some radiation leave a system, that is cooling. That's what you are going to see. So it's interesting. The cooling thing can be seen. So it will be seen in our case like what is known as background radiation. Any direction you look at, you will find some amount of radiation which is coming from all these gas, which are all different things are cooling. Star is cooling, gas is cooling, all this can be obtained. So you have to cool them, but not just cooling is not sufficient. You have to also make them denser. That means you need to do something known as fragmentation. So all of them has to have the sizes, because we see stars of size like sun, we see stars of size 10 times sun, we can see stars of size 0.5 times sun. So this has to be done also. So there is some mechanism. This has to be done through some perturbation, some scales dependent perturbation which gives you clumps. So you start cooling. This cooling leads to something known as instabilities. So different kinds of instabilities are there. They lead to star formation. So you have to track this. So start with the dark matter, put the baryons in it, let them cool, somehow fragment and all, they form stars. So this you understood. When you start stars, you start worrying about various things. One is energy. Because energy it is created, nuclear reaction create energy. That is what is visible to you. What is not visible to you is that nuclear reaction also changes the complexion of the material. You start with hydrogen, helium, lithium only. But if nuclear reaction happens, these things are fused to give you carbon, nitrogen, oxygen and heavier elements in the central regions. The star formation consequence, there are two of them. There are actually three, but one is light. Second thing is that you are enriching the element. Third thing is that when it dies, you also give energy back to the system. So these are the three things you have to remember. Okay. So this is what you start with: intergalactic material, cooling, star formation, nucleosynthesis. Of course, then stars are, this created material can also come out in various forms. One of the things we discussed about supernovae. Supernovae is one such process where you can throw large amount of material outside the galaxy. But some stars in intermediate stages also there are planetary nebulae, all other things which can also leave. So you have to worry about how you can remove mass from a star during its lifetime. So all the process should be incorporated. For example, sun, you know the solar thing, solar wind is there. That is one way of losing mass. But that is very small amount of mass, like it is 10 to the minus 6 solar mass per year or something. Like it's not much. Right? It is much if it continuously emits for a million years, because that will be mass again. But that is a small amount. But if you take slightly bigger star, then it can also go into a stage known as planetary nebulae, and that can also lose. Very massive stars will give you supernova. So this part has to be tracked. When supernova occur, you will also worry about whether the supernova can remove some gas from my galaxy and throw it somewhere, or it can still preserve this. That means you have to look at the dynamics of gas all the time, whether any gas particle in your galaxy satisfy the condition of escape velocity, right, or escape energy, so that it can go out. So this is the thing you are tracking. Of course, then again, suppose if nothing happens, this gas goes out of the star, it tries to do something, but gravity overwhelms, it can come back again, then it is ready for forming the next generation of stars. Okay, so this is what is known as a sequence of star formation. Star formation can happen. So what is the difference between first set of stars and subsequent set of stars which are formed? First set of stars will be mostly dominated by very light elements which are produced from the Big Bang itself. But the second set of stars, they are formed from the material which came out of a previous generation of star. So it will have additional elements like carbon, nitrogen, oxygen thrown into them. So when you look at the second generation, you will find that traces of these heavier elements. If you go to the third, fourth generation, this heavier element proportion will keep on increasing. So it is interesting way of looking at it. So you have to track all these things so that you can understand all the observations one see here. Okay, so I'll leave this, and this is what we are interested in. So this is the picture I explained to you in words. We start with something like Big Bang, and we have some kind of density fluctuations which are created, and we have to start these fluctuations. Somehow you grow and get into kind of galaxies which we are talking about. We have to get them into galaxies which are in different shapes, and if you go to the higher order, you will say that not only shapes, how they are distributed in space should also be decided, because there is we can go on and on, because there are a lot more constraints in observations compared to what I am talking about. I am talking about forming one galaxy, but if you are talking about forming set of galaxies, you will also ask how they are distributed. Are they randomly distributed, and how their intergalactic separations are changing as a function of time itself. So I am just switching to JWST. I think this may be a correct time. Okay, JWST. But just let's focus on few things. So you can, if you have some time and if you have some curiosity, just to take a few numbers you calculate, and it will be interesting. We said like we need material to fall into the center, or material to collapse into a smaller region where you can form stars. You can do this experiment. Take our galaxy, okay? Go to the edge of our galaxy. Let's say edge of our galaxy may be 50 kiloparsec from the center. You know that how much mass is there, and you distribute the mass in some form. Okay, even that is not needed. You can even take a uniform density. Take our galaxy, assume that it is uniform density, distribute the mass in a uniform density in a sphere. Just ask this question: if somebody wants to fall from this edge of the galaxy to the center, how much time it will take? This is easy calculation to do. Please do this exercise, and you will find that it will be of the order of 2 times 10 to the 8 years. So it's not like, because we are not like light, so light itself will take some time. Right? So we will travel with, at best we can travel with speed, sound of speed, and we can calculate what is how much is the distance, how much time it will take for you to fall. So 10 to the 8 years is for one particle to fall like this. If I want to change dynamics, at least few times interaction should be there. It's like a simple pendulum, right? One swing is like this, kind of. So this is interesting problem to remember. That's why this 100 million year is an interesting number to remember. If you take a star, if you form a star, how long it will live? Typically, right? Star dies. So if you take 10 solar mass a star which is 10 times or 8 times mass of Sun, it can go into supernova over a time scale of 10 to the 8 years. Again, so this 10 to the 8 in some sense is interesting. 10 to the 7, 10 to the 8 years is like our least count in the physics problem. Either you're thinking of falling into something, or I'm thinking of I form a set of galaxy stars and I'm going to change the stars into different forms of stars and all. How much time one generation is 10 to the 8 years, but I cannot talk of something 10 to the 6 years if each star is living for 10 to the 8 years. You see, this is like a least count in our method. That's why this becomes interesting. So I will just, maybe I will not go into the details. I wrote down few details, but JWST, what it does, you know that James Webb is in space. It is like a 6-meter telescope which is observing in the infrared. It is extremely sensitive because there is no atmosphere surrounding the atmosphere is pretty less, so it can see things as limited by optics. There is no other distortions which are there. So it measures very faint objects, right, at a high sensitivity. The faint object means the most distant object will appear faint to us because it is far away from us. So it starts measuring galaxies at distances very far away from us, and then these are the deepest images this JWST has produced. This is one of the deepest images, and you can see that the small thing which you are seeing in a normal case, you will say they are stars. Here most of them end up being galaxies. I mean, that's because the field of view is very small, it goes very deep. The number of stars you see is not, and they also choose the region such that there should not be bright stars. If bright stars are there, what happens? It will not allow you to expose longer. So that is the thing which is being here. Of course, it also produces beautiful spectra. That is the thing, because since it's 8-meter telescope, you can look at this object, for example. It appears like this, and if you take the spectrum, this is the kind of spectra one is getting, and you can identify a couple of spectral lines. There are techniques. You can, again, I will, if there are questions, I will come to during our discussion, but I will not say. They identify spectral lines, and the spectral lines now tell that these objects are at the spectra are shifted by a factor 13, 14 on the way. The highest thing one has found is the spectrum is shifted by factor 14. So what is it? What does that mean? This is what is known as cosmological redshift. What is cosmological redshift? Your wavelength, what you observe, will be shifted by some amount. This amount is much larger than 1. So it cannot be a velocity, right? In simple terms, it cannot be velocity. The way you understand here is that if a spectral line shifts by factor 3, you look at an object, the spectral line is shifted in wavelength by factor 3, what you understand is that this photon is originating from an object, and it took a lot of time to travel from that object to me. During this time, our universe, when the photon was originating from the object, the universe was slightly smaller. By the time the photon reached me, the universe has expanded to some size. The rate by which the universe has expanded is what is related to the shift, okay, wavelength shift. So this is, of course, if you are convinced with this, I will not explain any further than that. The redshift what we are measuring is nothing to do with any velocity. You can show at redshift 0 at local universe, it can be like a velocity, but it's not velocity, right? It's expansion. So the rate by which the universe has expanded is quantified by the amount by which the lines are shifting. Interesting, most of the lines which you are detecting in infrared is coming from, originally they are emitted in ultraviolet. The photon which is emitted around 1215 angstrom, if it is shifted by 10 times, right, it will be around 12,000 angstrom instead of 1200 angstrom. So this is very interesting kind of. So what do we mean by this? So this is what is interesting for us. If you take a standard cosmology today, you can ask this question: if I find some photons are shifted by a factor something, what is the age of our universe? These models will tell you connection between, if I live in a universe, if I send a photon from a universe which was 100 million year old, how much shift I will see if I detect it today. Okay? So this is what this curve is giving. Just for example, if a photon is shifted by 13, the age of the universe at that time is 300 million years. This is the problem I wanted to pose. And if the same thing is around 7, it is about 800 million years. So typically, the galaxies which are detected by JWST, they have shifts anywhere roughly around 9 to 13 now, mostly concentrated around 9 to 10, and we can clearly see that these galaxies are in a time scale where we are just, if I form one set of stars, they would have barely gone into supernova, from based on whatever we have done. So this is why you keep hearing the problem that JWST is detecting large number of galaxies, and these galaxies are already they say signatures of carbon, nitrogen, oxygen. It is not that these galaxies are just showing hydrogen emission. The fact that they are showing all the emission coming from different atoms means that not only these galaxies are there, they have gone through several cycles of star formation. And I am saying that one cycle requires 10 to the 7, 10 to the 8 years. Several cycles means it's already saying that you should have pushed this. You are beginning to question what kind of universe we are living in. Is this curve correct? Can I fix the time and now alter that my Big Bang model is wrong, and I have to change something else if I look at it in a simple way. Let's look at my whatever I call galaxy formation or star formation in a simple way. So I have just given the overview of problems which are involved. What is the kind of observations which are getting available, how it is just pushing the standard paradigm of galaxies into a difficulty. So you can clearly see my background is from astrophysics and mostly from observational astrophysics, now turning towards theory. So I am saying this as difficulties and challenges and things like that. If you come from background of cosmology, you will say that this is another tension. They will say Hubble tension, sigmoid tension, galaxy formation tension. So this is kind of, for young people probably, we are all already vulnerable to tension, so we should avoid this word tension. So we are not going into it. Having said that, is it so bleak? Okay, so the approaches one can take is very interesting. First of all, you will start questioning before drawing conclusions on the observations and questioning about the challenges we face. One can start questioning the observation itself. Are they measuring it correctly? Are there any uncertainties involved? Are there any biases involved? And things like that. Other thing we can do is that we also want to build, I just move on because I just highlighted various things. Other thing we can do is that shall we put all these things into numerical simulation and try to ask the question that can I address these challenges in a simple way? Do I have the same amount of density fluctuations I would need so that the number of galaxies JWST is seeing, I will be able to see it in my computer. Second thing is that what kind of prescription I have to do so that whatever galaxies which we are seeing in the sky can be produced in real life itself. So these are the challenges we have taken. So we are using our high performance computers. I have not put a lot of results here, but I will just summarize what is the present status. Present status is that maybe next week, sometime next month, sometime we will have a proper conference where we will present our latest results in IISER only. At least my student will be there to present. The bottom line is that we are able to run such simulations. We are able to simulate a universe which is very small. Our universe will be 100 megaparsec volume. We are not going to create the full universe. But each particle will be something like not a star, it will be like a globular cluster. This is what we could do at this stage. And I must say that it is very close to what is being done by other people. So this goes by the name Ninja. This is IISER IUCAA new simulations of JWST, galaxies and quasars. Okay, we can clearly see why did you do this. This was going to produce Ninja because we were discussing in one of our Zoom meeting what name to give. My collaborator has a small son, he said call it Ninja, so we said okay. nothing more is involved than this. And this is one of this code is originally developed by various people in US and Germany, and we are just modifying this to make it more flexible for us to do. So basically it takes care of galaxy evolution, it takes care of the supermassive black hole. We can see the black hole and look at the dynamics of the black hole. it takes care of chemical evolution, it takes care of the winds and other things, but we can control the properties of the wind. We can do various things which are involved. And it also takes care of, since it is, even though it is not a full universe, it also takes care of what happens around each galaxy. This is what is known as intergalactic medium. We also know how intergalactic medium is changing depending upon what we do with the galaxy. So I think these are the people involved. And just to put you in this thing, these are kind of benchmark simulations which people do. And I just wanted to focus on two things: what kind of scales they are simulating, 100 megaparsec, 300 megaparsec, 50 megaparsec, with around 2000 cube particle put in. Our simulations basically cover now 50, 150, 200 megaparsec. But there are two sets of simulation, one with 1000 particle, this is what we run in IISER, another with 2000 particle, which is run in IUCAA. And in fact, it is clear this is almost matching with whatever we call illustrious engine. So, if people have any idea of this simulation, is a very popular simulation. A lot of nice pictures are available for you to grab from them. So you can get it. You can produce your own thing using our simulation boxes. So just give an example, so you can see that we are not doing bad. We can. This is the full box squeezed into a small size, and you can look at the galaxies, and you can also see. You can produce these are all simulated galaxies at redshift 5. So what is the bottom line? So I don't want to, because if I want to introduce results, I have to explain all these things, but I can tell you what are we finding. We are able to manage a lot of observations up to whatever we call redshift 10, because I think we are, without doing any wild physics variations, with whatever everybody will understand, whatever everybody will agree to, we are able to do it. So if we go back to that plot, that will be useful plot to have. So up to this universe, up to this region, which means that anything beyond 500 million years, we are able to see that there is no issue. Because the issue are there because people who claimed issues, they have claimed based on semi-analytical models, which we need not trust. Okay. So you make a mistake. It's like I usually tell this thing: if I give a collection of points, you can fit it with a straight line. So straight line requires only intercept and slope. You can fix the intercept and slope with very high accuracy. But if you look at the plot, the line may not be going through the points at all. So this is like forcing some equation on a distribution which may not be correct. Right? So I feel that the problem like overproduction of galaxies, efficiency higher than 100% is needed to produce galaxies. All these are to some extent, not completely, to some extent related to the simplicity of simulations, which simplicity of analytical models one uses. Whereas why we have problem in producing these things? Again, this is remarkable for us, right? To understand universe, I fix everything starting from 500 million year to 13 billion year. Everything is okay because I have a model which explains everything. Only first few years we have problem. So do you now go and change the whole thing? So this is the question, right? 90%, 99% of the time you are right. 5% you are not. Now you say that I will change, CDM is wrong, Big Bang is wrong. Will you do this? So this is what we are exploring. So what we figured out at this level, I already explained to you, the free fall time is 10 to the 8 years. Typical stellar lifetime is 10 to the 7 years, 10 to the 8 years. So if your simulation has a resolution of 10 to the 7, 10 to the 8 years in your time step, or if you are dealing with masses which are 10 to the 6, 10 to the 7, not one solar mass, you run into difficulty. So what we are trying to address now, before saying that there is an issue in the early universe, we are trying to see that whether your simulations are converging in physics. If I put some physics and if I get a result, I just slightly change. I should not get very different results. It's like a stable point, right? Fixed point, stability calculation. You just perturb your relationship and see like whether you are getting back the same relation or not. Interestingly, we are not getting back that relation, which tells you that there is a numerical convergence issue when you want to address this very early universe. So we are now focusing on not only us, and I realized that when we figured out that what to change, there are papers appearing from other groups saying that they are going in the same direction. We want to resolve the physics much better. But the problem is when you try to resolve much better, your computer limitation will make your volume over which you will do this exercise smaller and smaller. So that is where we are. So hopefully at some stage this will be also sorted. So I just wanted to convey that in IUCAA we are able to run simulations. This is very recent actually. Run simulations and also able to get realistic results. Maybe at some stage there will be seminar at IUCAA or in this thing you guys can attend. It will be proper seminar where our results will be presented. And that is the situation now. But we are also looking for, there are a lot of things can be done with this data. For example, black hole growth, what happens to the black hole, how you reach, I just give an example, right? If two black holes merge and form a bigger black hole, it will give you gravitational waves, right? You can predict, our simulations give you this idea how much mergers per unit volume per unit time you can have. One can produce, that's why he even coined a simple thing, take a black hole at some redshift, you can ask what fraction of the black hole growth is dominated by gravitational wave emission, how much is by electromagnetic wave emission. These kind of calculations can be done, and there is a lot of things for people to look into. So I will stop here with this, and if you have any questions, these are just what can be produced. I don't have, okay, these are details, okay. Stop here, okay, thank you. You have any questions?
How does the emission spectra of objects help us in astrophysics? Like, what's the significance of we use it to predict?
Predict what?
How do we use it to predict patterns and all the observations?
Yeah, so the spectra is everything. Without spectrum, you cannot do astrophysics. This is the strongest statement I will make. Okay? Because to start with, you find the distance of the object. Second thing, I will give an example. If you find a spectrum and you find the total amount of emission in hydrogen atoms, that you can say that okay, if you know the transition, if you say that for this transition to occur, the probability is 100. That means if I detect one photon, that means it's coming from one hydrogen atom, there must be 100 hydrogen atoms there so that I get one photon towards me. Okay? So that means if I know that transition probability, you can go back and calculate what is the total number of atoms. You can calculate the mass. Okay? And if you look at the width of the line, you can calculate what is the velocity dispersion in that region. If you calculate similar thing, calculate the number of hydrogen atoms, calculate number of oxygen atoms, you can calculate what is the metallicity, how much is the enrichment, how much of the baryons have gone through star formation. So everything, this is a strong statement, but I strongly believe without spectroscopy you cannot do anything. These are all other things are not very.
Thanks for the nice talk. You talked in the earlier slides about density fluctuations and then more mass is attracted and something falls. Is that the same thing that gives rotation, or what gives the rotation? That wasn't clear.
Rotation is related to the net angular momentum in the system. See, the rotation what you are getting, that is related to the net angular momentum. For example, there are two sets of configurations stars can form. One is that suppose you imagine there is a collapse occurring. If the collapse is completely symmetric, there will be no angular momentum in the system. But instead, if you have a region where your stars are formed, and subsequently the mergers which you see, the gas can come from some channelized thing, it definitely brings a momentum into the system. So when the gas comes and collides with this gas, so it's actually the angular momentum of the collapsing thing will be reflected in some form as the rotation. But the pattern you see in the rotation is come from different modes of perturbations there. If you excite different modes, they can go to spiral and other things. But if you don't have anything, if you have a collapse of a spherically symmetric thing with very little angular momentum, you will have this whatever you call elliptical galaxies, where individual star's motion is governed by its angular momentum, but net angular momentum may be very small.
In your simulations, you you seem to be looking at structure formation and then formation of these galaxies. but you also outlined the problem that the composition of galaxies in the earlier part of the universe and at farther redshifts is not as early in the lifetime of the galaxy as you expect. Will these simulations have that information as well?
It addressed that.
Okay.
But we are still seeing whether it is addressing properly or not, because every time stars die, we also count the elements created and you add them in the problem. There is an inventory of elements are also there. Overall, we see the pattern of starting from only hydrogen and evolving. That overall pattern is there. But we are going even further than that. For example, how these things are created, whether it is created by alpha capture elements or whether it is created by rapid R process elements. So all these can be tracked also. So how many supernova 1, supernova 2? It's interesting actually. This is the industry which is going on for 30 years. I started doing it only now. So people have fine-tuned all this for lower redshift. Only thing we are addressing is that whether this is properly captured at the very early times.
So you mentioned that you perturb the model and then there is a convergence issue. Could you please repeat that?
So for example, I don't go and perturb it. So we can do like this. Suppose I start with a small box and I have some initial conditions. Then I find masses of these clumps are formed. I look at the distribution of this clump. How much clumps per unit volume is there within the statistical uncertainty. I just, instead of taking 1000 particles, I can take 900 particles or I can take 1100 particles. Everything else is same. I'm just saying the small changes in the composition of the particle. This tells you about the convergence in number. Second thing I can do is that if I take a region which has same amount of dark matter particle, okay, and it's starting from the same initial condition. Now question is that whether star formation has occurred at the same proportion. Because if you want to go in depth, actually these are numerical things, right? There is no physics is happening. We'll just assign some numbers, or it's like in your Python code, you will add some index to it. If index is filled, that means it has become star. You can say if index is 0, it is gas. Suddenly you say that it passes the threshold, it becomes star. You understand? We are not having star physically there. This is like just playing with an array and you filling that different arrays with different things. Temperature also like that. You are just changing the number. It's not that it is changing. When I said convergence means what we are asking is that if you repeat the exercise, either you start with different initial conditions or you just change the number of particles in the box or number of size of the box slightly. We want to see whether we are getting, statistically, if you look at the probability distribution of a particular quantity, they should have the same thing. They should not diverge. This happens at later stage. If later simulation you take, if two galaxies, two dark matter has similar thing, you can find that the way in which the chemical evolution has occurred, way in which the supernova feedback has occurred, they are all more or less, they should not be same because they have to be susceptible to the other quantity within that. But when very early times, if we are simulating not with very good timing resolution, spatial resolution, we are finding that factor 2-3 variations. That is where is the worry. You run one model, I get some number, I change something and run something else. This is nothing to do with regions being different, because there are 2-3 things. One is that you simulate a high density region, you simulate a low density region because you are simulating small. That could give difference. Here we are not talking about it. Everything, dark matter properties are same. We are just looking at whether stars and other things are there. So we are hitting what is the resolution issue. That's
I have a very simple question. Does dark matter also fall into a black hole, and will it emit radiation when that happens?
I am not the right person to answer this. Usually it will not, but there are people, in fact, since you asked, I'll say that people are talking about a neutron star capturing dark matter, so black hole can capture also. But we don't look into this.
From this model, can we say roughly at which generation a star is born, such that it has high enough elements to create components for life, let's say sodium, calcium, potassium, etc. And which generation was our sun born in?
Yeah, that is done because we don't need this model. In fact, sun thing is well documented. In fact, that is a completely different topic altogether. In our galaxy, there are stars with different ages. You can look at the oldest star, you can look at the youngest star, and when you look at the star, you are just seeing the composition of its photosphere. Photosphere is the outer region. Outer region never goes through any star formation. Outer region does tell you what was the situation of the gas in the galaxy when the star was formed. So if you look at star with different ages and look at what is the composition of its surface, that will tell you what was the composition of our galaxy as a function of time. It's very interesting problem. So this is what is known as age metallicity relation. How metallicity in a star changing as a function of age. This can be mapped to redshift metallicity relation for our galaxy. If you take it, this is like if you in a global sense, if you form our sun, if you take the age of the sun and look back and say where it should have been so that I will receive light today, it is around redshift 0.7, 0.6 to 0.9 depending upon which cosmology you take. And if you take average universe chemical composition at that time and compare it to its sun, and one can say whether the chemical evolution is progressed in the whole universe exactly the way it has progressed in our galaxy. So these are the kind of problems which has been addressed. So I will not say whether it's exactly matching, it should not exactly match, but I think galaxy like Milky Way will produce sufficient amount of chemical enrichment like what we see in sun by the time our universe was around redshift 0.5, 0.6.
And so if the higher
It is, if you want to say, maybe 3 billion years back, or 3 gigayears.
So if the higher elements proportion keeps increasing and increasing in the stars, so that's nuclear fusion, right? So can it go back also, like nuclear fusion, because we need more hydrogen, right, for the stars to keep burning?
No, there is no need for hydrogen because you will go into other. This is what I mentioned. You can go into capturing alpha, right? You can go from carbon to oxygen, silicon, magnesium, not by capturing hydrogen. You will start, because capturing hydrogen has a problem. You don't know whether deeply there is a problem. Hydrogen doesn't have neutron. So if you are using hydrogen to form a heavier element, there is always a problem. You have to convert one neutron into a proton. So that's why if you want to build elements very easily, you would rather capture helium. Helium has 2 neutrons, 2 protons. Hydrogen-based nuclear reactions are extremely slow.
I have 2 quick questions. One is that in your simulations, do you have to worry about whether your black holes that have to come at the center of the galaxies, so do they form through the direct collapse mechanism and then galaxies closer up?
We do some bit of cheating because since we don't form stars individually because our star particles are like star clusters. Our black hole is also seeded. So at present we don't have this stellar mass kind of black hole in our simulation. We assign some physical condition. If a particular region satisfied, we put a seed black hole in the deepest point of the gravitational potential minimum, and let it grow by accreting matter around it.
So at what redshift do you initially put these seeds?
You can put at any redshift as long as, so in our case we have a mass cutoff. Any region which reaches sufficient mass in dark matter we can think of putting. And we also want one generation of stars to happen, then we put it. So this is very fuzzy, it's not very clean.
And secondly, so you said that when you form stars from gas in a galaxy, the gas first has to be fragmented, and then you form tens of solar mass stars. But so why can't we have like a million solar mass stars? Why does the gas have to be fragmented?
Million solar mass star is always a problem because for a million solar mass gas, you start with million solar mass gas to form a single star. That means there is a center where nuclear reaction happens. The whole thing behaves like a hydrostatic equilibrium is very difficult because it requires from the initial condition perfect spherical collapse. If there is small amount of angular momentum, it will not it will not go to that kind of density, you cannot do this. Second thing is that when you are doing this, if you introduce small perturbation, you will start forming islands where the density will be higher compared to this, and those guys will become a separate object. This is the kind of problem on phases. In fact, this is not a problem, this is what the physics you use to form planets. Because a lot of this parent cloud, when it collapses, lot of fragmentation should happen. Only big fragment will become star, rest of them will become planetesimals and they grow. But if you want to produce a bigger thing, we have to avoid all these things. That means like we have to avoid small scale. So people try to do it with keeping uniform densities or smooth densities through various physical processes. So it's very easy to do this in an analytical thing by saying that I will seed with kind of thing, but in reality it is very difficult to do this. So there are a lot of conditions needed to have a collapse of monolithic collapse of a very massive gas without fragmenting is a big problem.
So you had mentioned that there are some studies about how even neutron stars have a certain portion of dark matter.
No, they capture dark matter.
Yes,
No, people talk about,
not having a certain portion, but that they capture dark matter. What I question is that, so how would we know the ratio? Because if amount of dark matter only interacts with normal matter through gravitational means, so how would we know the ratio?
No, but all these cases people introduce some amount of hand waving cross sections. So then they fix the cross section by demanding something. So I don't know, I heard that if two such objects are nearby, you will have some signatures in the gravitational wave, bring down signatures. So neither I know dark matter nor I know gravitational wave, so I will not comment on this. Yes.
If there's no other question, can I ask you? So you start your simulations with some
The perturbations like
Perturbations.
exactly constrained by observations.
yeah. So in at the magnitude of those perturbations, is there anything limiting you to what size object you can form?
Yes. Because we set up the perturbations. You can think of like it is all discretized based on the number of particles we are putting. See, you have 100 megaparsec. If you have 1000 particles, but you see that our resolution is 100 kiloparsec only. So it's not the correct way of saying, but for understanding it is better. Which means that we are smoothing some fluctuations which are smaller than the scale which is set by the resolution of the simulation. That is the first problem. Second thing is that the fluctuations are in all scales. So since we are having a box, we don't have modes of perturbations which are bigger than that box. So we don't have large scale power. We smooth the small scale power at some scale. So this is a problem. This is where this convergence issue comes. Are we having the correct resolution so that you capture a particular physics of interest? So this is a bit complicated. So we have to play with things to figure out.
What does intergalactic medium consist
Intergalactic medium mostly consists of hydrogen and helium, mostly. But people detect heavier elements. That is what is telling us that some of the material from galaxy might have also gone in a region between two galaxies. So, in principle, intergalactic medium has magnetic field. People have found cosmic rays in intergalactic medium. If you are thinking in that way, it has a lot of energy because it's a highly ionized plasma. And one thing you may not know, most of the baryons created, they are in the intergalactic medium. They are not in galaxies. Galaxy has only few percent of baryons. Rest of them are in intergalactic medium. That's why I spent all my life studying intergalactic medium. Only now I moved on to galaxies. Yeah. Okay.
We'll take some questions later. You can ask sir later. So, on behalf of Aakashganga, IISER Pune, I would like to thank Professor Srianand for the insightful talk. And now I request our faculty coordinator, Sushmita ma'am, to present a token of appreciation.